So what I want to finish up today is two more critical exponents in mean field theory. And I'll talk a little bit about phenomenological Landau theory, which is your question 2 and 4, essentially, on this assignment. And then we're going to introduce the Hubbard-Stratonovich transformation, which we'll use to, I think, sort of derive a more flexible framework, which includes fluctuations in order parameters, which will recover mean field theory, so what we're doing right now, but we can also use it to extend this sort of theoretical framework for, as John Carty called it in his talk yesterday, connecting the UV to the IR, right? That's basically what we're doing in this class. So we're looking at UV. So mean field theory you can think of as a long wavelength theory in some sense, okay? And we'll show exactly how this connection is made after we do the Hubbard-Stratonovich transformation. And the Ising model, the starting point, is like the UV physics in that language. So just to review what we did last class, we defined an Ising model. So interactions between sigma I and sigma j and an external magnetic field. And then the sort of crucial assumption of mean field theory, the thing that gave us mean field theory was assuming that we can neglect fluctuations. And it's fluctuations of the fields sort of around the mean value, which is the order parameter or the magnetization for this Ising model. So we took this to 0. And that sort of defines mean field theory in this context. So when you get rid of those fluctuations, the mean field Hamiltonian that we were left with look like that. Magnetization, right? And just a sum over a term that comes from, we assume translational invariance when we define J. So it comes from the interaction piece. And then there's also a magnetic field piece, which you can combine. And that gave us a free energy. I think I wrote this at the end of class last time. And we got this log of the hyperbolic cosine by taking the trace, remember? Something like that. And then the magnetization. So the strategy here was the magnetization is given by finding the minimum of the free energy. Okay, so principle of least action somehow. And so we took a derivative of the free energy, solved for the magnetization, and we got the mean field equation. So MJB over T. MJ plus B. Okay, so that's the sort of nonlinear equation that you have to solve to get the magnetization. So we defined some critical exponents, and we calculated 2 last time. So let me define this reduced temperature. PC is just some constant. It's non-universal, which means it depends on the UV physics, if you want to say it like that. It depends on the specific Hamiltonian, how you connect the spins, in a lattice or whatever it is. But the reduced temperature is just your distance from that critical point. And so far, we've calculated the magnetization critical exponent. So m goes as reduced temperature, some exponent beta, and the mean field value for beta was 1/2. Remember, just square root of T minus Tc. And then the end of last class, we calculated the susceptibility. So to get the reduced temperature right, I'll write it like this. Absolute T to the minus gamma, where gamma is 1 in mean field theory. Okay, so corrections to these mean field exponents, as I said before, are one of the main calculations that we're going to be doing in this class. So let me go on and calculate 2 more mean field critical exponents just from this basically simple free energy, okay? And then we're going to set up the problem a little different. We're going to start wanting to allow small fluctuations in the order parameter, okay? And that'll change sort of the, I guess the technical way we do these calculations. But before then, let me do 2 more. Let's do 2 more. There's a critical exponent that's defined basically by the dependence of the order parameter on the external field B, okay, that we have in that Hamiltonian. Let's look right at the critical temperature, and let's imagine varying the magnetic field B. Okay, so let me take that hyperbolic tangent and expand. Like I said last time, tan hx as a cubic term. Which, from that mean field equation for the magnetization, ends up giving Tc What's J over Tc? One. Remember? That's the mean field solution, right? So this term here is just m. We got m, m. So we can solve this for B, the B field. So it's just some, mean field equation. We've just substituted T for TC, essentially. And we have a way of relating the magnetization to the variation of the magnetic field. And the thing to note, with the trick with this calculation is just that when B is small, TC is just some constant. So you have two terms. And when the magnetic field is small, this term dominates. The 1/3. No, it's the third root or whatever. So the first order, or the leading order, can be written as small b to the 1 over delta, where b is like the reduced field. And delta is the mean field value of the critical exponent. You know, that determines how the order parameter varies with respect to this external field. So it's more like a response to the external field. Okay, that's a simple one. I don't tend to use delta all that much. But I think in more advanced theories, the point is this dictates how, you know, the response to a field that's lowest order, that couples the lowest order to the order parameter, right? So in a ferromagnet, you have some ordering, some symmetry breaking. The external field is the thing that couples directly to that order parameter. Okay, that's really, I think, what defines delta. If you have a more complicated order parameter, okay, so for example, if you had an antiferromagnetic state, if you had a plus sign in front of your Hamiltonian up there, you know, a magnetic field wouldn't couple the same way to that order parameter. You might need a staggered field or something like that. Okay. So that would be the analogous case.
So is this valid only for small B over TC?
This is valid for small because we've eliminated this term here. Yeah. But in general, there's an expansion, and you can define different exponents for different terms in that expansion.
Again, hyperbolic x must be very small.
Right. Yeah.
Near the TCM is small, definitely, but B over TC is not necessarily small.
But we've assumed B is small. Yeah. So right here. I mean, this is like supposed to be the behavior right when you approach the critical point. And you have a phase diagram that has, you know, temperature and magnetic field. Yep. But so is, you know, you have B and T, and there's some critical point, and you can approach it various ways. You know, you can come in all sorts of ways. So what we've held is a temperature fixed at TC, and we're looking at how we approach it on the axis. And infinitesimally close, there's a divergence. That's what defines the critical exponent. And that divergence is governed by this equation here. So the exponent is the universal object, or the universal number. But you have to be in that limit where you just approach that critical point.
So even with that assumption, we can say delta is universal. Delta is the universal.
Delta is universal, so this form here is sort of the universal form that you expect, right? And if you look at a full solution to this, you'll get that divergence to leading order, but the delta will be different than what we've calculated here, because this is just the mean field critical exponent. So when you include those fluctuating terms, they'll actually affect the value of that delta. But this is the expectation for the universal number. The order parameter goes to the reduced field, where the field is the external parameter that couples directly to the order parameter to first order. to the 1 over delta. So you can say this is the definition of delta here. M goes as b to the 1 over delta. Along the critical isotherm, right? You have your temperature fixed, and you're on this critical isotherm. This specific heat's the last one I want to do. This is the one that we'll actually encounter most in experiment, but it's also the one that's kind of most nonsensical in mean field theory. Oh. So again, approaching the transition, I want to use, what do I want to use? A definition of, let me just remember how this works. So I'm going to call it CV, just to distinguish from other C's. So that's the partial derivative of the internal energy with respect to temperature at fixed volume, say. Let me write that in terms of the entropy. Those are all at fixed volume, but partial U is just T, partial S, right? So this will give me T ds dt. And right, and S is the partial of the free energy, or minus the partial of the free energy, so with respect to temperature. Sorry to derive this, I just want to make sure I get it right. So yeah, so second derivative of the free energy with respect to T, and I have a free energy density. Well, I have a free energy up there. Big F is the free energy. So I could also say that this is, if I want the specific heat per spin, per latticite, it should be specific heat per latticite that's what I should have defined as CV. So this is the extensive CV here. Right, so this should be minus T, second derivative of the free energy density. Something like that. So because I have a free energy expression in mean field theory, so I just want to take derivatives to get the specific heat. Okay, brush up on your thermodynamics if you, or maybe I should brush up on my thermodynamics. So let's start with I think I can just do this straight away, but let's start from the free energy density. So we're off the critical isotherm now. Of T cubed M4. I'm just trying to write this as T minus TC, so. Okay, so near TC, the only thing that really matters is the difference, this difference here, right? Near the critical temperature, that's your parameter that's changing. That's a thing that's going from positive to negative. Remember these free energies that I drew last time. So let's simplify things. Now I have free energy written in terms of magnetization, which is my variable, m squared, m fourth. You'll see that many times in this class. And to derive m from this, just like we did up here, you take the derivative of f, set it to 0, look for the minima. So m squared you see that beta coming out? I guess I just rederived beta for no reason. Let me just finish writing here. And let me plug this magnetization into my expression for the free energy, or the free energy density. Okay, so that's the value of the free energy at m, where m is the value of the order parameter that minimizes it. Okay, so then my specific heat. Oh, which one do I want to use? So this is free energy density, right? So specifically for lattice site, needs a second derivative. What I should get out, something like this, T over TC. Almost too simple. This is valid in the regime where T approaches TC from above, or so when the reduced temperature small t goes to 0 plus, say. And that's under the assumption that the magnetization in the mean field sense looks somehow like this. Right, so m is equal to 0 above, and m is greater than 0 below. So below the transition temperature, if I approach that critical point from the other side, in mean field theory, I would assume there's no fluctuations. I just have a 0 magnetization there. So I can say and greater than TC, okay? So we write this as so in the nomenclature using the reduced temperature, I would write this as something like absolute value of the reduced temperature raised to the power minus alpha, a constant which I've previously ignored, but we sort of need for this case. So in mean field theory, this alpha, if this is the general definition, like if this is how we write the specific heat, in order to define a universal number, which I'm calling alpha, then alpha is 0 for the mean field theory. Because what it looks like is you have a discontinuity at TC. So it grows up to the value of 3/2. then jumps to 0 at TC. Okay, so you have this sort of unsatisfying case where alpha is 0 in mean field theory. And again, that's the specific heat critical exponent. That's all I'm going to bother deriving in terms of critical exponents. For the mean field theory, because there's two more which are very important. The critical exponents associated with the two-point correlation function of the order parameter, but we're going to treat those specially. Okay, so let me summarize what we've calculated so far. So the definition first, and then the value. So for the reduced temperature, T minus Tc, behavior as T goes to 0, near the critical point. So near a second order phase transition only. The magnetization, the first thing we calculated, for the external field, so the field that couples directly to the order parameter is 0, goes as reduced temperature to the beta for T less than Tc. And again, above Tc, we assume no fluctuations. There is no magnetization. Okay, so that's a simple one. That's the order parameter. Beta is the order parameter exponent. The susceptibility, which is, the fluctuation in some sense, it's the response of the order parameter at 0 field and finite temperature. I'm going to define a critical amplitude. What do I say in your assignment? C. It's C plus or minus. Oh, that's why I put CV on the specific heat. So pass me. I already thought this through. So I'll say that there's a amplitude above and below the transition, where plus is for, so it's going to be T greater than 0, and minus is for T less than 0. So the specific heat has a divergence that occurs on both sides. We've calculated one, the simple case when the magnetization is finite in class, and what you're doing on your assignment is calculating the other case where the magnetization is 0 in the mean field sense. So you're getting a feel for how that calculation goes. So that means there's two critical amplitudes, okay, the coefficients in front of this term, which you can also calculate in mean field theory, and you're looking at the ratio of these two terms on your assignment. So susceptibility you can define like that, the specific heat. So in principle, even though the magnetization is 0, you can play the same game. So it's T to the minus alpha, and I've added a constant here. But just because alpha equals 0 in mean field theory, you got to start thinking about what comes after it. And the same notation, I just called the critical amplitude A in this case. 1, 2, 3, what else did I do? Oh yeah, the critical isotherm. So that's the order parameter. It's like the case where you're at T equals Tc, but you're varying the external coupling that couples directly to the order parameter. Reduced field to the 1 over delta, so we define that. Let's call it critical isotherm. And the other two important critical exponents that we haven't calculated yet, so the two important ones for classical stat mech. We're going to start setting the stage for the formalism to calculate these now. And these are related to the spin-spin correlation function. So 2-point connected correlation function. So let me define it. G. So now we have a lattice, or we have some system, and we have to define the notion of spatial separation of the lattice points. So there's two spatial positions, Ri and Rj. So whatever those, there's maybe a spin here at site 0. There's another spin at whatever the coordinate of that site is. So we're just going to call those positions of those two lattice points Ri and Rj. And the 2-point correlation function is defined as, we'll make so it's 2 points. It's unlike the order parameter, which is just the expectation value of one of these sigmas. We have 2, therefore it depends on their separation distance. And for reasons that you'll see, we want to consider the connected piece. So we're subtracting off, you can think of this as basically the background magnetization squared, right? So it's like each one of these is like the order parameter. There's a good reason for why we're doing that, which I'll tell you later. Then you can define a critical exponent. And you can define a length scale. So remember I told you the most important concept for understanding the RG is the concept of a length scale. And that length scale diverges somehow at the critical point. That leaves you scale invariant. And that's where universality comes from. As Carty said, in 1 + 1, it also leaves you conformally invariant. We'll talk a bit about conformal transformations. And in 2 + 1, I think most people believe that critical points that are scale invariant are also conformally invariant. But as far as I know, there's no proof of that. So CFTs also come from this starting point. So I have a 2-point correlation function. So we will see that. What do I want to do? So let's go away from criticality first. So reduce temperature not equal to 0. Then my 2-point correlation function, which can be a function of temperature. So let me just say this is T not equal to Tc. Goes somehow as an exponent. Over some power law decay. Okay, and we can use tau there, but tau is just some power. It's something like d-2. It depends on dimension. So it's not a critical exponent in the sense that I'm talking about. I'm just using it as a blanket term for a more complicated exponential dependence. But you're dominated away from the critical point by this exponential behavior here. So it's e to the r, the separation distance, over the length scale, or the correlation length, which is the sort of fundamental object that I've been talking about in terms of length scale. So it's called correlation length. Kind of defines the envelope for, the cutoff of where your correlations, are no longer, where your two spins are no longer correlated. So if you're in a ferromagnet, or if you're in some more complicated state, you can imagine near the transition temperature, this spin might be correlated to this one. They could both want to be spin up, especially if your Hamiltonian's local. So the interactions between them are strong, so they want to be facing the same way. As you move way farther and farther in space, you'll start to decorrelate these two spins. And the length scale at which that happens is just defined by this calculation that we're going to do on the two-point correlation function. And this psi is the definition of sort of the envelope of that, where those correlations fall off to zero. I mean, it's an exponential, but. So it dominates this behavior, although we'll calculate this full form. And at t equal to 0, so right at criticality, your correlation length will diverge. I'll write that next. And this isn't as general anymore, but I'll just say it's an amplitude. Where I've defined an anomalous dimension called eta. We'll be doing this calculation on a d-dimensional hypercube. So there's two different forms for this correlation function. Okay. Even in mean field theory, we'll be looking at how this comes out. The anomalous dimension I'm going to come back to. We're not going to see it again for like a month. But in that intervening month, we'll be looking more at the correlation length. So the correlation length is the thing that diverges. You can imagine it has a temperature dependence. And I'll call the critical amplitude kappa for some unknown reason. So this is the definition of the correlation length isn't an exponent, it's a length scale. And this is the exponent associated with it, which is called nu. Okay, so oh yeah. So sort of importantly, as the reduced temperature goes to 0, this correlation length diverges. Okay, so the critical exponents that are universal. That we'll consider. Alpha, beta, gamma, delta, nu, and the anomalous dimension, eta. And these are the sort of the fundamental mysterious objects that we want to understand, in relationship to universality. And there's also critical amplitudes. I'll just make a note here. You're calculating one of these in your assignment. We're not as interested in these amplitude ratios. So C plus over C minus, maybe that's the one you're calculating. C plus over C minus, you have critical amplitudes A and kappa. But the exponents is what we're most interested in. So just so I don't keep you in suspense, let me write a table of the critical exponents for these Ising-like spin systems. I remember Ising models are, when we're talking about magnetism, we use the word magnetic field and so on. But Ising models can refer to any system that has, you know, a binary variable on a lattice site. So hardcore classical particles that are occupied and unoccupied and so on have the same Hamiltonian. So. So look back to this table from time to time when you lose track of what we're doing. So I'm going to list all these exponents. And I'm going to list some of its known values, so the values we just calculated. And the ones that we haven't calculated yet for eta and nu. And then I'm going to look at two different cases that are known exactly. So let me get these in the right order. Alpha, beta, gamma, delta. What do I have? Eta, nu. So we just calculated 0, 1/2. This is 3. What was this one? 1. 0, 1/2, 1, 3. The anomalous dimension, we'll talk about lots. It's 0 in mean field theory. And the correlation length, critical exponent nu, which we'll calculate shortly, is 1/2. So these two we haven't done yet. Now I've written down the most accurate known values that I could find, presumably with a 30-second web search. Delta should be big, 4.82. That's for 3 dimensions, and for 2D they're different. Delta's big, 15, 1/4, and 1 for nu. Do you know how these are calculated, these exact values? Basically Onsager solution. Like what you're doing in 1D in question 3. There's an exact solution for the two-dimensional Ising model. These are the values of the critical exponents. So they're different than in 3 dimensions. You know, these are calculated. Yep. Either series expansion or Monte Carlo. So they're done numerically. There is no exact solution. They're different between dimension. So that gives you a clue here about what, what dependence these exponents have. So they definitely depend on dimension. You should believe that they depend somehow on the symmetry of the Hamiltonian. When you look at equation 4, or question 4 on your assignment, you're constructing a sort of Landau theory for a Hamiltonian or an order parameter with different symmetry. But you're going to be talking about the mean field exponents. So keep in mind that there are exact exponents that you're not calculating in that question. The mean field exponents, we'll find out, are actually exact for d greater than or equal to 4. So there's a dimensional dependence, but we don't see it in what we're calculating. But I'll just give you the answer. Question?
Yeah. The delta for the D, is it 15?
Yeah, I think. That's what I wrote like 2 years ago. I know they're big. Deltas are always big. Oh, yeah, these don't quite line up. That's delta. So what matters in terms of the critical exponents is the spatial dimension, the symmetry of the Hamiltonian, if you will, and the symmetry of the order parameter. That's what determines what universality you're classing, to use the parlance of. So what do I want to do? Let's say I want to start deriving a framework for mean field theory where we can allow the order parameter to fluctuate. Because as we know, it's fluctuations of the order parameter which make the difference between these crummy values and the exact values that we would like to develop an approximation for. So this Ising model, again, just to hammer this point home, this is a universality class. Okay, this is one universality class. So even though we're mostly going to stick to the Ising universality class in these lectures, different symmetries and so on, mostly in your assignments, we'll be exploring different spatial dimensions, different symmetries of the Hamiltonian, different symmetries of the order parameter. They'll lead to different values. But for example, if you find a phase transition in some system and you don't know something about it, like one of the symmetries or the dimension or something like that, if you can calculate one of these numbers at that critical point, you essentially know what universality class you're in. Because these are essentially unique. Some of them maybe, you might want to be careful with some of them, but if you calculate delta in some system at the critical isotherm and see that it's 4.82, you know that that's in what's called the Ising universality class. And you know the dimension. It's a three-dimensional Ising universality class. That immediately tells you what the order parameter is. So you can basically use this table backwards. So for example, we've been talking about magnetism, but if you went back to this original motivation for the liquid gas system, you'd find the same critical exponents as the Ising model, which tells you something about the order parameter and maybe the dimension of the liquid gas system. Let me talk a little bit about phenomenological Landau theory before we move on. I don't know, logical. I've been talking about connecting microscopics with macroscopics, or the UV to the IR if you want. But the general form of the free energy that we've derived, where's the most telling version of it? I think it's behind here somewhere. With m squared and m to the 4. Yeah. I mean, we derive that from microscopics in principle, but you don't need to. If you can just guess what the symmetries of the system are, or the symmetries of the order parameter, then you can construct a Landau theory, it's called, which is just a mean field theory, where those parameters aren't related to the microscopics. So that 1/2 T minus TC, 1/12 TC, that's somehow related to that microscopic Ising Hamiltonian, and that's the mean field approximation. But we don't need, in principle, that microscopic model to write down a Landau theory. So that's just a note. I'll say without a specific Hamiltonian. Microscopic. All we need is basically an order parameter and knowledge of the symmetry or the invariance of the Hamiltonian. That's what I'm asking you to do in question 4. I want you to think about what a free energy is when you have that, do I call it a field? Unit vector, so it's a ON model that has some unit vector with different components. And we have to assume certain symmetry, like in the Ising model we have, remember, time reversal, so up-down symmetry. The Hamiltonian obeys that. The original Hamiltonian obeys that. In the ON model, if you have vectors in 3 dimensions moving around, there might be some rotational symmetry at high temperatures. And from that, you can just write down, essentially, an expression for the free energy. And by the way, this is basically what field theory is. Field theory, you're calling M phi. You're calling it an order. You're taking an order parameter that has a certain symmetry, and you're writing down a free energy, which is like an action. If you take 733, we just call them actions. And with symmetries, you write down that free energy, and then you basically just solve, just in the same way we did for mean field theory, that free energy. So we need an order parameter, knowledge of the symmetry of the Hamiltonian, and then we can write the form of F. Free energy density. So in our case, we have an order parameter. It's the mean value, if you will, of all the spins. And if we know that the Hamiltonian is invariant under Z2, or time reversal, or spin flip symmetry, then that's enough to write down the free energy. Means that the free energy, which we're writing with respect to a variable that's the order parameter, which is the magnetization, has to be invariant under that symmetry operation. And at low temperatures, what happens is you have spontaneous symmetry breaking, basically that invariance. Okay. So then the Taylor expansion recovers the free energy in the phenomenological theory that we just derived with microscopics. And the Taylor. And the Taylor expansion is what I would have written down before, and I'll just put some maybe R plus U. That's probably what I call them in 733. And studying, okay, so we can't have any odd terms. That's the point. With no magnetic field, there's no odd terms. Because of this invariance. If we don't have this invariance, we have to be more careful. You'll look at other, so in question 2, you're just looking at a phenomenological Landau theory that has a linear term in M. When do we know how to stop the expansion? Okay, so this M squared plus M fourth, we derived it there. We didn't go any higher. So we stop the expansion when we know that our system is is stable. And what stability means for us is that the free energy, as the order parameter goes to infinity, is positive. So we've already seen this. If we plotted the free energy versus magnetization, we had two curves previously, one for t greater than Tc, one for t less than Tc. Oops, t less than Tc. So remember, this shape here is when the parabola is upside down, which means r is negative. So in our phenomenological theory, r is just a parameter that changes sign at the transition. That's just a postulate of the theory. Doesn't even matter what it is. It goes to 0 at t equals Tc. And then the M4 term has a parameter in front of it that we don't care about in this case. That keeps your system stable. It means that you're in a local or global minimum here, not a global maximum, right? If it was upside down and you perturb the system, the ball would roll down to infinity. And that's what you don't want, right? You want to have stability and bound states and so on. So if for some reason u changes sign, like it does in equation or in question 2, then you have to have another term in your Landau theory. And the next highest term, the next highest order term, which isn't odd, is M6, right? So then you're free to change the sign of both of these, and stability is guaranteed by the higher order term M6. So this is a very simple theory. It's called Landau theory, phenomenological Landau theory. But it's like too simple in some sense. Oh, let me just write that down. That last thing I say, require that u is greater than 0. Anyway, what the question is asking you is whether or not there's room to get any other exponents from this. Okay, so if I had a different Ising model, very different, some different lattice, something like that, I had the same type of Landau theory, obviously I'm going to get the same mean field exponents. I'm going to get these exponents from that free energy. I'm just constructing a free energy based on symmetry. What you're doing in question 4 is you're constructing a free energy for an order parameter and a Hamiltonian that have different symmetries. And what I'm asking you is what the exponents are. I'm not asking you to solve the free energy, just asking you to write down the free energy in this form and then to argue whether or not you get the same or different critical exponents. Okay, so like I say, don't do too much work for question 4. It's more thinking. Any questions on that? Once you finish question 4, you can call yourself a field theorist. Because they basically don't do anything besides this in a more sophisticated way. Okay, so I want to quit using big M. Because the field theorists won't take us seriously if we keep using big M. So we have to call it phi. And one reason for changing notation now is because we want to quit thinking about an order parameter that doesn't fluctuate. So I want to start putting in a mechanism where we can let the order parameter, which, the magnetization, fluctuate. And so I'm going to generalize this Landau theory. Beyond means fluctuations. So we'll still connect to the microscopics. We're still going to connect to the Ising model, okay, because this is a condensed matter StatMech class. So, but just keep in mind that, you know, other treatments, especially ones you see in high energy and so on in field theory, they won't always connect to the Ising model. Okay, so in some sense, it's it's a mechanism to keep yourself grounded in reality. But let's consider starting to put in fluctuations. So m's not fixed, but it's just a simple parameter. Simple parameter. With respect to which the free energy is minimized. You know. So in particular, it can be non-uniform in space. And it can also, I guess, have thermal fluctuations. So right now, we just have a thermal, m is just a value for a given temperature T. If we solve that equation, m equals hyperbolic tangent, whatever, mj over T, we just get some curve. So we say m is a certain value at a certain temperature. But let's start thinking about a thermodynamic ensemble where you can have a mean value, but you can also have fluctuations around that value. And it fluctuates with T. Okay? That is a field. When people say field, in field theory, that's what a field is. It's your order parameter that has fluctuations and it's non-uniform in space. And a variable like phi or whatever that denotes a field is just really just the spatial dependence of the order parameter thing, and it just distinguishes it from something that's uniform in space without fluctuations. So let's start from the order parameter and develop the theory. So we can still interpret things in this concrete way with the Ising model. With partition function that has a trace. I'll just write it like this: sum over all spin states e to the minus beta h. H you can just substitute in that Hamiltonian. So again, you have this difficult problem. E to the minus 1/2 t, so 1 over 2t. I think it should be plus. Minus minus is plus. Sum over ij, jij. That's a problem you can't solve. The infinitely complex trace. So we're going to do something. We're going to generalize the Gaussian integral in order that we can write this partition function in a different way, and in a way that we can take that trace. Okay. So not right now we can't try. I mean, try it. I encourage you. But in general dimensions D, you can't take that trace. So we're going to use the Hubbard-Stojanovic identity. Which I'll write like this. For a system with n spins, So I'm just going to write it in general in terms of some real variable, phi, and some matrix A that's invertible in a specific way, and some other real number. These are sigmas, but I want to keep them as real numbers now. I'm going to call them gammas. We're going to see why we need this integral. But this thing is equal to okay, where the phi's are going to take the place of m in the way we're thinking. These are going to be the order parameters that have spatial dependence and fluctuate. This identity is true for general real numbers, any arbitrary real number, gamma. We're going to identify gamma with the Ising variables in that Hamiltonian. Okay, so these are going to be our, I'm actually going to write these as sigmas, but the identity is true if they're any arbitrary real number. And, you know, just like the sigma, expectation value of the sigma gives m, phi is the, again, somehow the order parameter associated with those variables. A is a symmetric real invertible matrix. Are all real symmetric matrices invertible? Seems like it, right? Okay, invertible it is. I just didn't know how to spell it, so we use an I. So the real matrix A is going to play the role of J, the matrix that tells you about all of your couplings in whatever dimension that you're in. Oh, and I have all these repeated indices here, which are actually Einstein summed. Sum over repeated indices. Who's seen this before? Seems like less people have seen it this time than last time I asked. I'm going to derive it. It's going to take me 20 minutes or 10 minutes. I don't know. You only have to see this once. Or if you're like me, you have to do it every year for the rest of your life. Every free theory is a Gaussian theory in the sense that you can solve it with a Gaussian integral. And so maybe solving is kind of a vague term, but you can solve for maybe two-point correlation functions, equilibrium stat-mech properties with Gaussian integrals. Let's start with what we know. A one-dimensional integral, which just means that the dimension I'm counting is the index on those fields, 1 to n. So if I just have one field value or one variable, x, call it, then I have a one-dimensional Gaussian integral. And I'm going to have two real numbers. And I can call this I1 for one dimension. And it's going to depend on my real numbers. I'm going to define this integral. over one variable. And I need, so it's Gaussian, so it's like this, 1/2 ax squared, I think. Yeah, and the b is the linear term, so bx like that. You know how to solve this, presumably. But when you have this extra piece here, so it's not just strictly an x squared in the argument of the exponential, there's just a trick, which is going to help us out in the n-dimensional case. Completing the squares and rescale x plus b over a, which is what occurs here. You can call that y if you want. You can call that y and then change this to dy. Why not? Uh-oh, plus or minus, what do I want? I think I want minus. And when I do that, dy is equal to dx, because everything else is just a real number, right? Then my integral becomes if I've done that right. Okay, so then you get that pure e to the x squared part and just this coefficient out in front. Okay, so let's do the same thing. For an n-dimensional integral. So I'm just going to define A and B. They're no longer real numbers. So A is that matrix. It's the same A that I've used over there. Invertible n by n matrix. But B couples to the linear term. It's going to be a vector. Real n-dimensional vector. And then my integral, I n a b, has n variables in it. So I've written with Einstein's summation convention, which shows you the similarity to the left-hand side here. But since I lose track of the indices, I'm going to do the proof with vector notation. So that x has to be transposed, big T. And this transpose vector B has a dot product with a vector x. Okay, so x vector is a vector of all of these variables, n of them. So far, so good. I've just defined the thing we're going to solve. So let's shift the integration variable. So at y was x minus b over a. So let's do the same. So x is equal to y shifted. So I got to invert that matrix. Call it a minus 1. So we got to get used to dealing with a and its inverse. This isn't the inverse of each element of the matrix. It's the inverse of the matrix elements. And we also need the transpose which you got to switch the order of B and A inverse. And that's because A is symmetric. So A minus 1, what transpose equals A minus 1. You can just do the proof. Complete the squares. So I'll just do it really quick. There's two terms. That first term, transpose A x. So it's x transpose A then x. Write these terms out. Maybe I regret all these vector notation things now. That's the first term. The second term, B, should be a vector, right? Transpose x. So it's the transpose vector dot x. I don't know if that's redundant or not. So then the argument of the exponential becomes very simple. Because there's a couple terms that cancel. Okay, so I'm talking about this piece here. Minus 1/2, sorry, minus 1/2 x transpose A x plus B transpose dot x. So change the variables, complete the squares. My integral is now, you can see that term coming out front. And the remaining integral over variables y. So we need to be able to solve this, which is our Gaussian integral, just like we did last time. We just knew it was root 2 pi over a. We just got to be a bit more careful with that. Right, there's some Jacobian associated with diagonalizing that matrix. But once we do that, we're pretty much set. So let me call that the integral n finite a, but b is equal to 0, because we need that. So let's diagonalize A. So it's a matrix, not a vector. And then we'll write the solution in terms of the eigenvalues. A is symmetric, so it's orthogonally diagonalizable. Spectral theorem. So in quantum, you might be used to diagonalizing with a unitary. Since it's a classical, you just diagonalize with an orthogonal matrix. O. So define some O, which you don't know what it is. As a matrix where its transpose is its inverse, -1. So then, the diagonal matrix is lambda. Has all these diagonal elements and zeros. That's a spectral theorem, I guess. That's just telling you you can diagonalize this real symmetric matrix with a real orthogonal matrix, O. And we need another change of variables. So this is maybe the non-obvious step. To V, it's just we've gone from X to Y. Now we're going from Y to V, where we've just when we multiply V by the orthogonal, we get Y. And note, when we change those variables, we have to worry about the Jacobian, which is the determinant of that orthogonal vector. Yeah, because it's n-dimensional. V. And since it's orthogonal, luckily this thing just equals 1. So the fact that it's real and symmetric is important, but we have to think about what that means physically. It means that our Jij's in the Ising model are real numbers, and then that matrix of values is symmetric, which means that I interacting with J is the same as J interacting with I. Right? So it makes complete sense microscopically, and it leads to this big simplification that essentially allows us to use the Hubbard-Stratonovich transformation. Okay, so then, just to finish off, write it like this. Lambda, which is diagonal, so we just have a sum. Lambda I, and so the elements of the diagonal and the elements of the transformed vector V, which contain our original variables X. So I can just write the final answer for b equals 0. Oh, that's an integral. Integral over v's 1/2 I equals 1 to n lambda I vi squared. All right. You can write this different ways. There's n integrals, which is basically what's going to help us simplify the trace for the Ising model. In this case, we can just use it to solve that integral. It's 2 pi over a, like we had in the one-dimensional case, but instead of a, it's all of the eigenvalues of the diagonal matrix, because we've diagonalized things. And it's a product of each one of those. So that's the equivalent of the 2 pi over a. So some people call this 2 pi. It's a square root, but there's n of those multiplied by 1 over the square root of the determinant of a. Okay, which is just this piece that contains these eigenvalues. Okay. Product of these things. So I'm going to write the final expression for A and B. Good, it took me 20 minutes, and we'll never do this again. We'll just start using this next class. That's what I started with, what I'm ending with. One half B. Right, the piece I pulled out front. Okay, so that's the Hubbard-Stratanovich transformation. Let's make sure I got it right. Yeah. Right, so this stuff usually doesn't matter. It comes in front of a free energy. What we're really going to do is we're going to take the Ising model next class and write it so that we decouple things into an auxiliary field, you might call that, X. You've integrated over that auxiliary field, so the price you're going to pay by taking the Ising model and turning it into this is you have an additional field and you have to do an n, where n goes to infinity dimensional integration. So we'll see that next time, and we're going to use the Hubbard-Stratanovich transformation to try to, rederive the mean field theory for the Ising model. Okay, so we're going to, again, everything on these chalkboards is just the proof that we need to start again with the Ising model next class. And once we do the Hubbard-Stratanovich transformation, we'll be in good shape to deal with fluctuations, because we're going to introduce this field parameter that's spatially varying and has thermal fluctuations. That's what's really missing with our previous mean field theory. Okay, so I'll see you guys Friday, and then a week Friday, this homework's due. Anyone still not have this? You want this? Okay, see you guys then.